Okay, so the next speaker is Yurii Pashkevich.
Okay. First of all, I would like to say thank organizer to invite me with this talk. This work was implemented by a big team, which is headed by Christian Bernard, which is located at the Freiburg University. And during this investigation, we big facilities which is available now in this European synchrotron radiation facility at Grenoble, and also diamond light source in Great Britain. We study Altermagnet properties of the cuprate manganite interface. First of all, I should mention about main important feature of the Altermagnet, of the Altermagnets. It is shown here. You see here that there is special symmetry operation which permute different magnetic site, and which permute the crystal field environment. So here you see this orientation of the crystal field, and here another crystal field. But in the most important feature, that in the local symmetry, in local environment, these two magnetic ions have the same orbital. And this is main prerequisite to get the special feature. This permutation allow us immediately create anisotropic spin density, and therefore in the momentum space, therefore any kind of charge transport along some direction immediately will feel this anisotropic spin density. We study YBCO manganite, cuprate manganite superlattice, which is created by pulse laser deposition. We get under doping, special doping, manganite, which is in insulator state, and CA type, and it has CA type and ferromagnetic codering. Whereas YBCO, our BCO present just optimally doped compound, which has TC around 80K. And what is we will study what is going on at the interface. What we expect in this case. In this case, we see that there is a connection through the apical oxygen between copper and manganite ion. This connection immediately lead to strong alteration of the electronic state, both manganite and copper ion. There are a few reasons for this behavior. One of them is the copper and manganite ion have different electronegativity. And another one, there are also two types of manganite ion. Because of doping of the manganite layer, we have the manganese 3 plus and manganese 4 plus side due to doping. So electronic state of the copper and manganite ion at the interface should be strongly altered. Therefore, we want to investigate, namely, what is going on at the interface copper-oxygen 2 layer. So I should notice here that here at the interface, this is namely copper-oxygen 2 layer, not a copper-oxygen chain. And we have some hint of what is going on at the interface because of we provide the study X absorption spectroscopy. which give us that at the interface we have a similar amount of holes with dx square and dz square orbital character. So this populate these two orbitals almost in equal value. What we get from our RX study about orbital and spin order of the YBCO interface copper layer. We see here that there is antiferromagnetic ordering, which is realized on the different orbitals. On the d square orbital, and nearest neighbor is z square orbital. So this is our conclusion based on the special possibility which give us RIX study. How can one probe orbital and spin order in a single atom layer using only RIX? We did not use neutron scattering or muon spin resonance. This is possible if our technique allows study of excited state above ground state. If we have this excitation above ground state, we can say something about detail of the ground state. In our case, such excitation are interfacial single layer magnons. For this study, we use almost all RIX advantages. These advantages stay energy scale, momentum scale, resonance sensitive to atom type and selective probe of its local site environment, polarization selection rules for scattering on a given type excitation. What about detail of this all enumerated advantage? Energy scale means that if we start to use your photon from the with Röntgen energy, with X-ray energy, we have RIX process which with intershell absorption from 2p shell to 3D shell, and subsequent decay from 3D to 2p decay. Because of this huge energy, around 1000 eV, it is possible to achieve any excitation in a crystal allowed underscattering process. They are phonon, magnon, DD excitation, charge transfer excitation. So this energy scale gives us unique possibility for studies. Next important advantage of the RIX is momentum scale. If here we see just expected value of our momentum for RIX photon which we use, this is 931 eV, which has this wave length, and it gives us respective possibility to move to the momentum space of crystal with given value of the length, which one can achieve here even boundary of the antiferromagnetic brilliant zone. So, and possibility to study of different momentum transferred to the particle, it is connected just simple rotation of the sample with a fixed angle of the scattering and outgoing photons. Therefore, we have here different value of the transferred momentum to the our quasi-particle magnon. You see here this one. And another important feature is elemental local environment sensitivity. This is a spectra which is shown in a big energy scale of our sample in the case of bulk and interface resonance. What does it mean, bulk and interface resonance? If we just change the value of incoming photon, and it is found independently, in previous study, we see that at some resonance, which we name bulk resonance, named shown here, we have different spectra of GG excitation. It is different in any direction of the scattering process. So position of copper GG excitation are different if we have so-called bulk copper ion or interface copper ion. Next important situation here, a possibility of RIX, is a polarization selection rules. If we want to study one magnon scattering process, we should use cross type polarization, which is induced spin flip process. So in here presented matrix element of RIX, which is contain this polarization of incoming and outgoing photon. Here we have a spin operator. Here we have structural factor. And what is important for our purposes, here is a form factor of magnetic ion, which dependent on the orbital state of ion. So this behavior for absorption of the cross magnon in cross type polarization is allows us to distinguish magnetic excitation in the RIX spectra from non-magnetic. Here we demonstrate two different spectra for bulk resonance and for interface resonance. You see here that this different spectra demonstrate strong change of the some excitation, which is seen when we have changed our frequency of incoming photon. So we see here that if we use so-called bulk resonance frequency, we see here big contribution, big line, which we name M2 magnon. And when we change our energy to the interface frequency, then we see a strong increase of intensity of some low energy magnon. So to say that it is really magnon, we performed here cross polarization scattering, and we see that in cross polarization situation, we see that this contribution from our magnon excitation completely suppressed. Now we have a result of our spectra, which is shown here by point, which you name M2 and M1 magnon. And this M2 magnon has typical energy, typical for spin wave branch for bulk YBCO cuprate. But there is a new spin wave branch, which is come from interface. And this observation is very unusual. And to try to understand what is going on, we apply a simple linear spin wave simulation with the only one in plane exchange interaction. So what we use here, this is so-called 2D Fossa lattices double layer Heisenberg model. And we apply here for the next to interface copper layer usual exchange interaction, and for interface copper layer we apply exchange interaction which should be different from the bulk exchange. And this two value should be fitted from to this spectra. So our fitting give us this value of exchange interaction. For bulk line magnon, we have exchange interaction which is typical for YBCO bulk magnum, which is very well known in previous investigation. And for magnon, which is seen in the low energy, we should use another value which is almost 2 times lower than the exchange interaction in the bulk. So how such magnon energy scale with an orbital order? So this is again typical spin wave branch and bulk new spin wave branch from interface. The answer is possible very simple. So if we consider just a value of the exchange interaction for the usual copper oxygen 2 layer, we have the same orientation of orbital, but in the case of interface copper oxygen 2 layer, we have decrease of the exchange interaction, which exactly follows by Goodenough-Kanamori rules, because of if we have here different orbitals, immediately from this rule we have decrease of the exchange interaction in such case. So the energy scale give us possibility to say that we have very special orbital state in our interface copper oxygen 2 layer. Next, quite interesting situation which we have here, we start to investigate the value of the behavior of the intensity, dependence on the change of transferred to moment.
Yurii, 5 minutes
Sorry?
you have.
Sorry?
You have 5 minutes to finish.
Okay. So we see that we can very nice describe the value of the behavior of the intensity for bulk, like magnon, but it is completely fail to describe this intensity if we use formula for matrix element with the same orbitals. But the situation can be very easy resolved if we suppose that this destructive interference completely disappear because of we have for one spin operator for up, for instance, with one orbital and another spin down, let's say, with orbital z square. If we apply this one, and we can calculate orbital form factor momentum dependence using single ion model for spin scattering. Then we immediately get very nice coincidence. So we have additional evidence that in our case, we have such kind of specific orbital ordering. So we have 4 evidence for our restored orbital state at the interface copper oxygen 2 layer. So this is magnon energy scale, cross-type polarization, most intensive spectra at interface resonance frequency, intensity anomaly due to special orbital order. So then it is interesting to consider possible theoretical models considering the implementation of the Altermagnet state in different orbitals. There is some paper in which Altermagnet arise due to spontaneous ordering dx square and z square, zx, dxz, sorry, and y of the orbital interaction and exchange interaction, there is possibility to create orbital ordered antiferromagnetic state which give altermagnet properties. Another situation considered here in this paper, which where altermagnet is based on the Vanadat family, which it is proposed have Kugelholmsky orbital ordering. And it has been predicted that such kind of ordering will give to the Altermagnet properties. So here we have also orbital in this case, and in this case we have orbital ordering in T2G subsector. And very interesting suggestion also appears for creation of altermagnets from ferrimagnets, which is stayed at the compensation point. And if this ferrimagnet based on the non-equivalent magnetic dimers or non-equivalent issues, then we get again, as shown in this paper, we will get again altermagnet properties. So now my conclusion is that we uncover new type of altermagnets in which an antiferromagnetic order is realized on the identical magnetic ions with different orbital state in EG subsector. So, this conclusion is based on properties of single-layer interfacial magnons, which were investigated for the first time in a cuprate manganite multilayer. And I would like to say personally thankful for the support of me by Swiss National Science Foundation through the individual grants program of the Scholar at Risk, which has enabled me to collaborate with colleagues from the physical department of the University of Fribourg. Thank you for your attention.
Thank you, Yurii. Question, please. You?
Yeah, I have a question.
Yeah, you don't have a question.
So thank you very much for the talk. One question would be, if you have this new orbital ordering, could you see that in resonant diffraction experiment? Is there any chance to go to the elastic peaks and see the orbital ordering?
Elastic peaks, which you mean Riggs elastic peaks?
I mean REX, so not RIX, but elastic scattering.
Because of elastic scattering, because of we deal with here with one layer manifestation, one atomic layer manifestation. Probably if we try to use this REX, I don't know, is it possible or not? Actually, I have not answer on this question.
Interesting to look at that.
It would be interesting to look, you will say. Okay, more questions online? Yeah, actually, I wanted to ask actually the reason why you use this heterostructure when superconductor and magnetic structure, right? What is the reason? To get proximity and to have this superconductivity? Initial reason to use such a structure?
No, I understood. We have here energy scale at which work only exchange interaction, and it is quite, of course, in the case of the optimally doped, we have poor superconductive state. But in the this energy scale, antiferromagnetic filtration is very strong. Therefore, we can say about this, if we want to say exactly detail, this is not a magnon, this is a paramagnon. So this is a paramagnon which we study here. And the conclusion about this round state, orbital round state at the interface layer, based on, first of all, absorption spectroscopy. And now we only add some details which comes from the Riggs studies. So this
So for you, it does not matter that it's superconducting or not now. Yeah,
Uh,
another.
The question about superconductivity of the interface layer is a very difficult question. And up to now, there is no consensus on this situation because of.
Speak about it later. Just we have experience measuring EPCO with ARPES and see that it's not superconducting the upper layer.